Welcome to Investigation 2, or Unit 2, looking more closely at the periodic table. So up at the top here, it talks about Dmitri Mendeleev's periodic table, and you have a bigger picture in your text that shows this old-fashioned periodic table, and it's got symbols of elements, and it's got some numbers on them, and those numbers are supposed to represent a relative mass, at least the best they could do at the time. You watched some videos on alkali metals, and with each unit we'll have some kind of an anchoring phenomenon that we want to try to explain by the end of the unit. So in Unit 1 it was fireworks and the colors of light. In Unit 2 I want to know why, if I look at like the alkali metals, number one, why are they so reactive compared to other metals? It's not a normal property of a metal to put it in water and have it like react somewhat violently. And a lot of metals don't react at all with water. They're very stable in water. So number one, like, what's up with the alkali metals being so reactive in water? And then number two, why as I go down the group do they become more and more reactive? And so can I use the periodic table to predict those properties and explain those properties? Now, you don't have to do this claim evidence reasoning worksheet. We're not worried about that, but that's kind of what I want to focus on as we go through this unit. How can I explain somewhat unique properties of alkali metals as opposed to properties of other elements? The periodic table is all about patterns, constructing explanations and making predictions about new patterns. So question 1 says, do you see any patterns in how Mendeleev's 1869 elements are arranged on the periodic table? Describe a pattern and provide an example. And so some of this is kind of just what you're thinking about as you look at this old periodic table. And it looks like he has elements in groups. So there's like a group with hydrogen and lithium. There's a group that goes from beryllium to sodium, magnesium downward, and so on. So he's grouped the elements. If I know anything about like beryllium and boron, carbon, nitrogen, oxygen, fluorine, maybe some of them are like non-metals. Maybe I could make a pattern with their masses. Like the first group, hydrogen and lithium, have kind of small masses, and then beryllium through sodium are kind of in the middle, and like maybe he kind of chunked them in groups by their mass. Maybe they're kind of by their properties, because then I see some of these bigger groups and it seems like it's a lot of metals like chromium, iron, nickel, cobalt, copper, zinc, and maybe some of the patterns are based on their properties. You could have any of those for number 1. Number 2, constructing an explanation. The periodic table has changed considerably since Mendeleev's early versions to our modern periodic table. What patterns displayed in these earlier versions of the periodic table drove the discovery of new elements? So here's one thing that we'll look at in a minute. Especially, like, take a peek at that first column, hydrogen to lithium. And there's just like a big gap in there. So is it that there were no masses at the time that were anywhere between 1 and 7? And so maybe there was just like a blank space left in case a new element is discovered that has a mass somewhere between 1 and 7? Maybe it's that, he left gaps. Like in that last column, there's some gaps. Maybe it's because the properties seemed to change in a pattern, and from bismuth to thallium, I should say the mass number, 210 to 204, and maybe he thought there were some elements in there that had kind of missing properties. All good stuff. That's kind of further explained by this crazy timeline. So the earliest known periodic table came from a guy named Wolfgang Dobereiner, a German chemist that organized the elements that they knew of at the time in triads. And so he just found groups of 3 elements that seemed to have really similar properties and grouped them together. Now, the key is that in the early 1800s, we obviously wouldn't have known of all the elements that we know of today. So this was at least one attempt at trying to organize the elements in groups of 3 based on their properties, and then kind of having similar masses, or masses that seem to kind of increase, and that if I took the first element and the last element and kind of averaged them, the mass of the middle element seemed to fall right in the middle. And next was a man named John Newlands in 1865. Newlands obviously then would have more elements to work with at the time. There were more elements known, and decided to organize his elements by octaves, or groups of 8. So again, he looked for 8 elements that kind of had similar properties, and seemed to find that if I went across by 8, then the 9th element seemed to kind of match the first. So I started with hydrogen, and then kind of started going across, and noticed then that if I have lithium, for example, as the second element in, and I guess that he could have called that element number 1. By the time you get to the 8th element, sodium, the properties are kind of similar. And so then that's how he kind of knew like when to start a new row, so that the elements would line up with similar properties, and eventually created groups of 8. That looks nothing like our periodic table today, obviously. So getting a little closer is this Mendeleev periodic table. Obviously still not anywhere near our modern periodic table, but there were some really innovative things that came from Mendeleev's work. Dmitri Mendeleev didn't care about groups of 3 or groups of 8. Instead, he kind of focused on the properties, and started organizing the elements, and wasn't afraid to leave some holes or question marks in his periodic table. You could also look at increasing mass, and kind of started organizing the elements that way, and found that, if I start with hydrogen and then lithium, and then go across to beryllium and boron, that often elements increase by mass. But if I have a large gap, or the properties aren't lining up well, he wasn't afraid to leave a gap in the periodic table. That's like pretty big time for a chemist in like the late 1800s. Think about like the lab materials and equipment that they would have had at the time. Pretty minimal. So question 3, how is the process of using patterns to predict phases of the moon similar to the process Mendeleev used to predict undiscovered elements? I'm just going to stay real simple with this, and obviously this is kind of what you were thinking too as you read through the little description on the phases of the moon, and I just say that it's all based on observations. People making careful observations, plotting that data, and then looking for patterns. So we're making observations based on the properties of the elements, or making observations based on the changing phases of the moon, and then being able to predict how that changes over time. Here, being able to predict what the next elements should be.